Hello, this is Mrs. Menard talking to you from afar. Today we're going to continue our discussion on writing electron configurations and drawing orbital diagrams, building off of our introduction to the quantum model yesterday. You should have out your notes. You should be taking notes as we go through this. This video will be shared with you through Schoology, so if you need to go back and re-watch parts of the video, you most certainly can do so. All right, so we're going to be looking at rules for electron configurations, including the Aufbau principle, Hund's rule, Pauli exclusion principle. All right, so let's do a quick review of our quantum numbers from yesterday. If you remember this chart, we have the energy levels 1 through 4. There is a max number of electrons that can fit in each of these regions that can be calculated using the formula 2n squared. So the first energy level can hold a maximum of 2 electrons. The only orbital allowed in the first energy level is the 1s orbital, and with only one orientation, the 1s orbital can hold 2 electrons. The second energy level can hold a maximum of 8 electrons, and that includes a 2s orbital and a 2p orbital. Again, the 2s orbital with one orientation can hold 2 electrons, while the 2p orbitals with 3 orientations around the nucleus can hold a total of 6 electrons. So when you add those up, you get the max number of 8 electrons in the second energy level. Third energy level can hold a maximum of 18 electrons. It's in the third energy level that we first see our d orbital. So we have a 3s, 1 orientation, 2 electrons, a 3p, 3 orientations, 6 electrons, and then a 3d, 5 orientations, 10 electrons. And then finally, we went through the fourth energy level yesterday. The fourth energy level can hold a maximum of 32 electrons, and this is where we introduce the 4f. It's the first energy level that can accommodate an f orbital. And there are 7 orientations with the f orbital, giving us an additional 14 electrons that can be held in the fourth energy level. We did look at 4 different quantum numbers. The principal quantum number is the energy level or distance from the nucleus. The second quantum number, or the angular momentum quantum number, represented by the letter L, gives us the shape of the orbital, the s, p, d, and f. The third quantum number, the magnetic quantum number, m sub L, gives us the orientation of the orbital around the nucleus. And then finally, the fourth quantum number, the spin quantum number, m sub S, gives us the spin of the electrons. While we're not going to be talking about these ideas directly today, they will still be in the background as we're looking at how we draw orbital diagrams and write an electron configuration. We do have rules for drawing our orbital diagrams. The first rule is the Aufbau principle, and this states that electrons occupy the lowest energy level available first. I lovingly consider the electron to be the teenager of the subatomic world, meaning electrons really want to exist at the lowest energy possible. It's not that they aren't willing to exist at a higher energy, but if there is a lower energy available, they're going to choose that. And like I said, I consider him the teenager of the subatomic world with love in my heart. Lowest energy level available first. Now, there are factors that affect the energy of an electron. One of those we talked about yesterday, and that's the attraction to the nucleus. This is an exothermic process. It requires no energy to be attracted to the nucleus. This is what we were talking about when we talked about the principal quantum number and the distance from the nucleus. But there is an additional factor that affects the energy, and that's the repulsion of other electrons. This is an endothermic process, meaning that it requires energy. The electrons have to have energy to overcome that additional repulsion. When we're talking about the energy of a given electron, we're taking into account both the attraction to the nucleus and the energy required to overcome any repulsion of other electrons in their same region. And so because of that, if we look at this energy diagram, you can see the nucleus there at the bottom, and then the energy is raising as we go up. Hopefully you recognize that we are drawing some dashes to represent the different orientations of different orbitals. And if we were only interested in the attraction to the nucleus, then chemistry electron configurations would be super easy because we'd go in the order that we would expect. For example, we would go 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 5s, 5p. However, because of the introduction of additional electrons and the repulsion, it's not that simple. So as you can see, when we're going up this energy diagram, at the bottom is the 1s orbital, which is completely what we would expect. Then we have the 2s orbital, and then at a slightly higher energy is the 2p orbital. Even though the 2s orbital and the 2p orbital are at exactly the same distance from the nucleus, because of the introduction of repulsion of electrons in these orbitals, the 2p is at a little bit higher energy than the 2s. Then you can see we have the 3s, and then again the 3p is slightly higher than the 3s, again because of repulsion of electrons. And then here's where we get our first kind of exception to the order. We fill a 4s before we fill the 3d. So you can kind of think of it this way. If we're at the third energy level, we have 2 electrons in the 3s orbital, 6 electrons in the 3p orbital. So in the third energy level, we already have 8 electrons. That is quite a bit of repulsion. So for the next 2 electrons that go into the 4s orbital, it is easier for them. It is a lower energy for them to go a little bit further away from the nucleus where there is no repulsion. So it's easier for them to go a little bit further than it is to push their way into the third energy level where there are already 8 electrons and quite a bit of electron repulsion. Then when we look at the 3d, which is the next orbital that is going to be filled, we have 2 electrons in the 4s orbital, so there is repulsion in the 4th energy level because of those 2 electrons. And then there's also repulsion in the 3rd energy level, which is a little bit closer to the nucleus. So for the next 10 electrons, it is easier for them to push their way in closer to the nucleus with the repulsion than it is to push their way further out from the nucleus where there is also repulsion. Now, this may seem kind of complicated, and it is a little bit until you get used to it, but we do have a shortcut. So you should have picked up that little quarter green sheet of paper. This is the Aufbau principle shortcut. As you can see, as you go across each row, we have 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. This is what we looked at yesterday. If you follow the arrows, it gives you the order in which our orbitals are filled. So the top arrow goes through the 1s, 2 electrons go into the 1s. The next arrow goes through the 2s, which has 2 electrons. Then the next arrow goes through the 2p, then the 3s, then the 3p, then the 4s. Now this is our first exception, which is why I put it in red. We're filling the 4s before we go and fill the 3d. Then the 4p, then the 5s, which is our next exception because we're going to fill the 5s before we fill the 4d. And again, this has everything to do with there being too much repulsion for our electrons to push their way closer to the nucleus, so they move further away from the nucleus. After the 4d, we have the 5p, and then we have the 6s, and it's after the 6s, sorry, that we then fill the 4f. So that's also in red because now we've put 2 electrons in the 6s orbital, and now it's easier for the next 14 electrons to go all the way back to the 4th energy level and push their way in, where we already have, 18 electrons already in the 4th energy level. Then we fill the 5d, 6p, 7s, 5f, 6d, and then the 7p. Now this shortcut is here to help you kind of get used to the order. You are not going to be able to use this half sheet on the next quiz that we have, but the periodic table is really your best cheat sheet. So you're going to use this little green sheet until you understand the patterns on the periodic table, which is going to be part of your processing tonight at home. All right, so there's the Aufbau principle. You kind of just have to accept the order in which they're filled. It has to do with not only distance from the nucleus, energy due to distance of the nucleus, but also the energy required to overcome any repulsion between electrons already in an energy level. All right,